So we are going to start in few minutes. I mean to say 1 minute or 2 minutes. So I think Professor Naresh is already there. So I think he's joined from Sri Chitra Tirunal. Hi, Professor. How are you? Hello.
Yeah. Hi.
Hi. So.
Is it clear from here?
Yeah, there is a voice breakage is there. Just you can speak few words.
Yeah, I actually can hear.
You can switch off the video.
Yeah, I have switched it on.
Yeah, while you can switch on. So later you can switch off because the bandwidth may not be sufficient for you. So
yeah, sure.
thank you. So that we'll also switch off the video. So
yeah,
that bandwidth will not be an issue.
yeah, sure.
So we are going to start the session. It is another 1 minute. It's at 7:29. So if all the participants, please note that we are on time. We are like so we cannot wait for somebody to join or something. Yeah, thank you. It's 7:30. The times tick to 7:30. So let me introduce about today's invited speaker, Professor Naresh Kasoju, who is working as a scientist in the Department of Applied Biology and Biomedical Technology wing in Sri Chitra Tirunal Institute of Medical Sciences and Technology, Thiruvananthapuram, Kerala. He obtained his PhD in biotechnology from IIT Guwahati, India, and postdoctoral experience from Institute of Macromolecular Chemistry, Prague, Czech Republic, and University of Oxford, UK. His research interest includes biomaterials and tissue engineering. He has published more than 50 articles with over 3,500 citations and an H index of about 20 and I-10 index of about 30. He is editor of 3 books, guest editor for 2 journal special issues, and editor for 1 journal, and reviewer for more than 50 journals. He has been recently selected as an early career editorial member for Bioactive Materials Journal. Impact factor is 14. So he and his team have presented work at several national and international international agencies, I mean to say, so international conferences, and received quite a few awards. He filed 6 Indian patents and 3 Indian design registrations. He has received a total of 9 research grants from internal and external agencies, including DST and SERB India. He is currently working on the cell sheet engineering of corneal tissues, 3D bioprinting of skin tissue equivalents, and bioreactor systems for large-scale bone tissue engineering, stem cell-based exothermal therapy for lung regeneration, and silk-based biomaterials for biomedical application. With this short bio, I request Professor Naresh to take over the session and enlighten our participants. Thank you, Professor Naresh, and the floor is now open to you. Thank you.
Yeah, thank you very much for the kind introduction. Could you confirm if you are able to see my screen?
Yes, we can. Yeah, audio and visual PPTs, everything is fine. You can go.
Great. A very good evening to all the participants. Indeed, it's my pleasure to be part of this ATAL faculty development program. And in fact, it is really timely workshop because 3D printing and 3D bioprinting, especially for medical device sector, is really growing significantly. And in fact, the government of India is very keen in promoting these sort of technologies, especially in the medical device sector. So it is definitely a timely workshop, and I profusely thank Dr. Ravi for giving me this opportunity to present some of the basics as well as our work that we are doing in Sri Chitra Tirunala Institute. So the topic is more of biology based. So I'm not sure. I understand that there is a diverse group of participants. So I'll try to make it as simple as possible and try to give you a flavor of the bio aspect of 3D printing and what kind of printability assessment that we usually undertake, including a glimpse of the in vitro and in vivo evaluation that we have done for one of our projects. So before I go to the topic, so let me take the pleasure of giving you insights of about my institute. So it is Sri Chitra Tirunal Institute for Medical Sciences and Technology. It's based in Thiruvananthapuram, Kerala. It is an institute of national importance, and it's a autonomous institute under the Department of Science and Technology, Government of India. So it is a hospital which is a almost 300 bedded, which is specialized in cardiology and urology. So we do have a lot of patients coming across all over the India, getting treatment in a very niche areas of cardiology and urology. And we also have a biomedical technology wing. So this is where the R&D part of medical devices being explored. We also have Achyuta Menon Center for Health Science Studies. So this is again a unique setup, which is looking into the public health aspect of various diseases and follow-up of various activities that we do. So it is a very unique combination of a medicine with R&D into the medical device technologies and also public health related aspects. So under one umbrella, and it is it's almost 4 decades now, and it has really stood the test of time. And this particular institute was particularly developed by our forefathers to do indigenization of medical devices. So we are talking of Make in India for the last 40 years. So Chitra heart valve, or this artificial mechanical heart valve, is the hallmark product of Sri Chitra Institute, and it's being done in millions of patients so all across India. So it has actually cut down the cost of the heart valve from few lakhs rupees to just few thousand rupees. And as I mentioned, so the first patient who has received this sort of indigenous heart valve is still surviving after like 28 years now. So that heart is still beating. So that actually gives you a flavor of the quality of R&D which has gone into the design and development of this particular heart valve. So not only heart valve, like the other associated medical devices in the cardiac surgery, open heart surgery, and something like oxygenators. So they're also produced in-house. And coming to the neurology part, so we also have shunt, hydrocircular shunt developed and marketed widely. We are also having a DBS program recently. Apart from that, there are quite a few cardiovascular related devices like vascular grafts. And we also have a very strong bioceramics group which develop composites for bone as well as dental related applications and various other products. These are just to give you an idea of the kind of range of medical devices that we develop. And this doesn't come just like that. So it actually has gone through a series of what do you say infrastructure development in line with the Indian as well as international standards. So we have laboratories which start. So our work starts from scratch. So we do the material synthesis, whether it is polymer synthesis or a ceramic synthesis or even other composites. So we then go for a physicochemical characterization. We also do the cytotoxicity assessment as per ISO standards, the hemocompatibility assessment, toxicology, histopathology, and microbial load or the sterilization related aspects of it. We also have a very strong team of engineers who do design verification. So quite a lot of in silico analysis also goes into the R&D part before we actually start fabricating in-house. Now, once we have these things, so we also have an animal facility, both small animals as well as large animals. So we have models, rats, mice. Then we also have large animals like sheep models as well as pigs. So we do quite a lot of preclinical evaluations in the animal models for assessing the safety as well as efficacy of the medical devices that we are developing. And once we have the product, so there are certain follow-up studies that you are supposed to do, including the sterility of your package, the pyrogenicity, and the residual, the composition of it, or the package validation. So quite a few tests starting from the material synthesis until the product is released to the customer. So there are quite a lot of things done, and these are developed in-house for the last 2 decades, and these are on par with international standards, and they are being accredited. Most of our labs are accredited by NABL in India, as well as COFRAC, which is a French agency, which is testifies for the quality of the labs that we have in terms of testing and calibration of medical devices. So these services are also offered because we realize that we are one of the unique laboratories. So we also offer services to other academic as well as industrial partners. So if any of you are interested in making some physicochemical characterization or in vitro or in vivo level assessment, safety or efficacy studies, so you are most welcome. We have established a channel through customer service cell, and all the details are available on our website, including the charges that we charge for different types of tests. So in this talk, what I thought was probably I'll give you a glimpse of the tissue engineering as such. So what is the need that we have to do this sort of fancy technologies? Then we also have to, I'll also give you some idea of basics of tissue engineering, including a couple of approaches that are very popular in the field. Then I will be also touching upon 3D printing, which I'm sure by now you may have a very good idea. But also I would give you a glimpse of what 3D bioprinting differs, in what ways it differs from the conventional 3D printing. I will give you some idea of a typical workflow in the field of 3D bioprinting, and also what are the popular strategies and the applications of 3D bioprinting in the field of biology in general. In the third part of my talk, I would also give you an idea of the bioprinting work that we are taking up in our institute, particularly on the printability assessment and the preclinical evaluation. So let me start with the first part, which is why do we need the tissue engineering concept, and how actually the genesis of tissue engineering has happened. So as we know, like we see in the news, as we read in the newspapers, that and we also encounter in our day-to-day life, many of our like maybe relatives or close ones, happen to prone to some sort of accidents, or the diseases or even age-related problems, which in one way or the other would lead to tissue loss or even organ loss or organ failure. So which at times are manageable, but at times are very severe, and sometimes it can be fatal. So the gold standard approach or the gold standard solution for managing such tissue and organ loss is obviously the tissue and organ transplantation. So if one donor comes forward, so he or she would be able to save up to 8 lives with the complete organ donations like heart, kidney, pancreas, etc. And even the small tissues or other tissues in the body can be donated, and almost 50 needy patients could be receiving those sort of tissues. So for instance, skin or corneas or other bone grafts or other particular parts of your body. So but unfortunately, if you look at the statistics, So if you go to the developed countries like Spain and US, so the donation ratio or the organ donation ratio is quite appreciable. Like, we have almost 50 persons per million who are coming forward for donations. But unfortunately, the figures in India are very poor. So as many of us, in fact, we are not very much aware of such organ donations, or we have never come forward. We never thought of in the first place to go for such organ donation movements. So this actually led to a very significant gap between the demand and the supply of organs. And unfortunately, if without other than this, there is no other solution. So there are no other products which are available in the market to counter this sort of tissue and organ shortage. So that is where the concept of tissue engineering has come up. And in fact, there is a famous picture of a mouse with a human ear on its back way back in early 90s. So that is when the genesis of tissue engineering has come up. So that actually includes three basic components. So it is called a tissue engineering triad. So where the first part is the cells of a particular tissue of interest. Then cells alone cannot really lead to a functional tissue. So at times we need to play around with the functions of cells by introducing some biochemical factors into the system. And apart from these cells and biochemical cues, you also need to think about some material which is called as scaffold. So these are certain biomaterials, biologically derived or synthetically derived, which are for medical applications. So, and they are formulated or produced in a particular shape or form on which the cells are cultured. So they can be cultured in vitro, or they can also be directly used in vivo. So these three components are used in multiple combinations and permutations by different researchers depending upon the need. So typical tissue engineering process involves, so for instance, you have a patient with a cartilage defect. So what you do is you try to take out a healthy portion of that tissue, and then you try to isolate cells outside the body. So you try to grow them, because what you need is for the treatment, you need millions of cells. So you may get hundreds, a few thousands of cells from a healthy tissue, but that's not sufficient. So you had to multiply, expand them in vitro in the cell culture facility. So you isolate the cells, multiply to millions of cells which are required. Then you seed those cells on these porous scaffolds. So these are again the biomaterials. And then you try to mature them into a functional tissue, and then you go for the implantation into that particular patient. So let me give you an overview of the three components which are involved in this tissue engineering process. So the first being the cells. So where do we get cells from for a particular tissue engineering process? So we can get the cells from various origins. So the first thing that we think of is obtaining some somatic cells, so which are like differentiated cells already. So when you talk about tissue engineering skin, so you can actually take the skin cells directly from a particular donor. So you can take a fibroblasts, or you can take epithelial cells from that skin. But where should I get it from? So you can actually go for an autograft. So if you have time, and if the cells are able to be proliferated in vitro, you can always go for an autograft. But think of a patient who has come with severe burn. There is no healthy sort of skin left out, and he cannot wait for you to take cells outside and multiply, and which will take a couple of weeks or even more than that. So when the time is not sufficient, so you have to depend on somebody else. So, and this is also commercially viable. So as a company, so if you ask me, so I would be more happy to ask for a donor who is healthy enough, and I'll try to develop as much as possible. I will try to multiply as many number as possible. And whenever somebody is requiring, so I can provide the cells off the shelf. So of course, we do have certain immunological challenges involved with that allografts. but then it is commercially viable, as well as it is more manageable when you have patients who cannot wait for a autograph based tissue engineering solutions. You can also have isographs where you have an identical twin, but of course, not many of us are fortunate to have a twin, so that's most likely ruled out in many cases. And people also think of xenografts, but as we all know, so we'll have very severe, significant immunological reactions. But these are the options which are available. So auto or ISO definitely will be advantageous, but when you have no time or less time, so again, you cannot rely upon, and you have a limited number. And as I said, like if a patient is having a severe a higher grade of skin burn, so you have very limited healthy tissue available, and certain cells in this somatic tissues have low replicative potential. So if you think of hepatocytes in liver or pancreatic beta islets or even neuronal cells, so you can isolate, but then you won't be able to proliferate to millions of numbers as it is required for a particular clinical applications. So you have to think of some other alternative sources. So that is where the concept of or these stem cells comes into picture. So stem cells are in a nutshell, or in a layman's language, are some cells which are having a magical powers to develop into any type of cells in our human body. So these cells are originated or available in different stages of our embryonic development, and all through the fetals and all through up to the adult stage. So you have certain cells in the embryonic stage which are totipotent, so which means each cell of this embryonic stage have the capacity to develop into a complete human being. But then the challenge is that you can't really disturb the embryonic stage. It is considered as very unethical, ethically incorrect. So we have very stringent rules not to touch or not to work with any sort of embryonic stages stem cells. But then you have some other stem cells in villi or amniotic stage or even umbilical cord. So these are cells which are having multipotency, which means they are able to generate into multiple cell types given certain conditions. And compared to other sources, so the cells sourced from umbilical cord are very, I would say, simple relatively, and they're also ethically less challenged because the umbilical cord is after the pregnancy, so it is just discarded as a bio waste. So instead of discarding this, so you can actually source that and try to isolate those stem cells from that cord, and that can be differentiated into a particular tissue or a cell of interest. So that is the one good thing about the stem cells isolating from the cord. And probably that is why you see that many of these hospitals are trying to encourage the parents to go for biobanking of these cord derived stem cells, because at some point or the other in the future there may be a hope to treat certain special or rare diseases if unfortunately the child encounters. We also have tissue-derived adult stem cells, even in adult stage. So we do have quite a lot of stem cells in almost all the tissues now. So you have cells in the blood, you have cells even in the adipose tissues, the fat tissues, and you also have cells in the bone marrow. So different tissues isolation will be little different, and some isolations are very easy. So for instance, you can just simply do a liposuction and then you can get rid of fat, as well as you can also get some stem cells out of it. But then isolating stem cells from bone marrow is a little bit tricky. So but then all the cells irrespective of the tissue source have similar potency level. So that is one good thing. So as the science is advancing, we are discovering more and more easier sources of these medical cells out of the body. But then, like you may have these stem cells, but then you can also induce the pluripotency in any particular somatic cell. So you need not really go for isolating, cumbersome procedures of getting bone marrow or getting fat or other things. You can actually just take a biopsy of your skin, a small piece of your skin, and then try to take out those fibroblasts easily, and then manipulate that into somatic or stem cell based systems by introducing some factors. So this is one. This is called that induced pluripotency stem cells. This is also one of the hot areas of work, which is taking a significant momentum in recent days. But having said that, there is no ideal cell source for regenerative or tissue engineering applications. So as I just mentioned, so each source has its own technological, ethical, as well as biological challenges and advantages. So it all depends on you, on the need of that particular patient, and accordingly you may have to take a decision which type of stem cells you want to go with. So the second part of tissue engineering triad is are the biochemical cues, so the biochemical factors. So as many of you know, the cell, there is a in our body. So where it is a liver cell or skin cell or whatever. So it is a functional unit of life. So it is viable on its own. But unfortunately, we are a multicellular body, and we are three-dimensional body as well system, wherein the cells need to interact with other cells for various purposes. So whether to just to have a structural support, or whether to have a functional communication, for various reasons. So the cells need to communicate with other cells, and this happens by basically two modes. So the first mode is through non-soluble factors or direct interactions with the cells as well as the matrix. So there is something called the extracellular matrix. So it is something like, you have a brick and then you have a cementing material. So bricks are your cells, and then you have this cementing material, which is a extracellular matrix. So there need to be a very good bonding between your brick as well as your cementing material, in this case cell as well as matrix. So this happens through the direct interactions through ligand receptor systems, and it is called a matrix-ring interaction. And then the cells will also shake hands with the neighboring cells through direct interactions, something like gap junctions, tight junctions, desmosomes. So there are different mechanisms or proteins which are involved. So this actually, try to have a physical shake hand with another cell and try to communicate and try to send its signals to the neighboring cell, and also to receive if there is anything from the neighboring cell. And then the other part is also having communication, but it is through soluble factors. So this is where the biochemical growth factors and other enzymes or chemokines, cytokines, and inflammatory, pro-inflammatory, anti-inflammatory. So there are quite a few biochemicals which are soluble in state. So they freely move around, and there are multiple types. So you can have an intracrine interaction. So wherein the cell produces something inside its own boundary, but then it consumes it for the sake of doing something extraordinary. Then you also have autocrine systems, so it actually releases a particular signal outside, and that released signal outside does something, reacts with something else, and then comes back, and it gives the signal back to that particular mother cell, and that is how you have some sort of a autocrine mechanisms. You also have paracrine mechanisms. So the neighboring cell try to release something, and it will be sensed by the receptor cells. And then you also have faraway signaling mechanism. So because when you pinch on your hand or some part of your body, you can immediately sense pain or other senses. So there's a lot of signaling which is going on from in an endocrine fashion. So it is the signal is produced in some X part, but then you receive the signal and you will sense that in Y part, and you have a that sort of a far-reaching effects in this endocrine systems. But all these things work in a simple mode of action. So you have a producer cell, it actually releases the signaling molecule, it travels through the extracellular matrix, and then it goes and binds to the receptor, and the signal is transfused to the molecular level, where a gene is either expressed or suppressed in order to give you a biological response. Now, this biological response are two types, both positive as well as negative. So when you say positive, so it can actually lead to cell proliferation. So whenever there is a damage, whenever you have a wound, so that wound is healed over a few days of timeline, because the signal that the damaged site is releasing quite a few molecules, and the neighboring cells, including some resident stem cells, will receive those signals, and they will try to encourage the cell proliferation to heal that particular. But you also have a negative effect of it. So you can also have signaling mechanisms which would tell you, like in case of cancers and all, whenever the cell is unable to control its cell cycle, it is inducing something called apoptosis. So it's a controlled cell death. So there is a mechanism to even kill the cells. But even the same sort of signaling molecules play a significant role. So the cell can also differentiate, or it can also de-differentiate. So when you say cell differentiation, so you have some, like as I said just now. So whenever there is a wound, so there are resident stem cells which induce or which are prone to differentiation into that particular skin type cells. Or if you have a bone loss, or if you have other tissue loss, so the resident stem cells will get activated, and they will try to differentiate into that particular target tissue cells. You also have de-differentiation mechanisms. So this is where again something related to the cancer. So you have certain cells which are supposed to be controlled cell cycle, which are supposed to have a controlled cell cycle, but unfortunately, you have there is no control over it, and they become de-differentiated, which means they go to a state of stemness and proliferate continuously, and without a significant control. And it could also lead to malignancy, because they can proliferate and differentiate into multiple cancerous types. So that is where you have a very worsened case of a scenario. So in a nutshell, it can heal a wound, or it can also lead to a wound. So it is very important to understand what kind of biochemical factors that play a crucial role in a particular tissue niche. And we try to replicate those sort of mechanisms by incorporating, if not all, a few of those molecules in your tissue engineering concept. Now, having said that, how do we replicate such release mechanisms or biochemical factor incorporation in the tissue engineering concept? So this is a glimpse, or this is a schematic showing you in a nutshell of various modes of biochemical factor incorporation in the scaffolding system. So there are certain non-covalent binding, and we have a covalent bonding. And as you know, so non-covalent are something which you don't have much of a direct interaction, and whereas covalent, you definitely have a direct interaction, and it requires certain activation or certain energy input in order to cleave that covalent bond. So even in non-covalent, you can have as simple as physical adsorption, where you can just dip your biomaterial scaffold in a solution of a particular growth factor, and these growth factors will simply adsorb onto the surface. So the advantage is that it is very simple, straightforward, one-step process. But then the disadvantage is that it is easily washable. So as soon as I mean, the bonding is very weak, so the release will be very quick and burst. So you can also go for something like ionic bonding or ionic binding. So where you have a matrix which is having some positive energy or a negative surface energy. So accordingly, you take a growth factor which is having a oppositely charged. So you have very famous this chitosan based coatings and other things, where you have this anionic and cationic interactions between matrix and the drug or the biochemical factors. So these are again also very easy, and you can also go for a layer by layer kind of a coatings in this sort of scenarios. But again, these are not that strong. So once you have a pH change, so they are able to again wash out very quickly in a burst fashion. You may also think of affinity binding, provided you have such an suitable uh, functional groups which can be clickable easily between your matrix and the growth factor. Then you have these encapsulation systems, which are just based on matrix entrapment. So this is more of a physical entrapment. So you have these biochemical factors which are just encapsulated in something called a hydrogel, for example. Then you can also think of covalent binding. So this requires a specialized enzyme or a pH change or any other condition which is intelligent or which is smart in nature. So these are some, prone to this responsive or thermoresponsive or pH responsive sort of a mechanisms requires for that release. Then you can also think of some interpenetrating sort of a cross-linking systems, which are more complex, and this will give you more of a sustained release. You can also think of encapsulating in a sort of a physical capsule. So you can have your entire solution, either liquid or semi-solid or a gel-like thing in a membrane or a cassette type of thing. So it all depends on the need. So again, nothing is perfect and nothing is universally accepted. So it all depends on the chemistry between your biochemical factor as well as your chemistry, the chemistry of your matrix, and the kind of release that you are expecting. So if you are looking for a burst release, a quick release, you can think of simple adsorption, but you want a controlled release and a smart or an instructive release. So you can think of this sort of incorporating some special bonds into it. The third component of tissue engineering is your biomaterials. So biomaterials are, as I mentioned in the very beginning, so these are like naturally derived or synthetically derived materials which can be incorporated into body tissue as part of an implanted device, or it can be used for treating some or replacing some bodily functions. So these are classified into four types conventionally. So starting with metal, so the most popular, the titanium based or other metallic implants, which are widely used in medicine, comes under that category. You also have hydroxyapatite based, ceramics and other ceramic glass and bioglass and other ceramic materials, which are also used in hard tissue applications. So that also is one of the popular class of biomaterials. Then widely used biomaterials are polymers, because you have a lot of the soft tissues in the body, and polymers are highly tunable to any tensile properties. So you can go for a synthetic polymers which have a very good control over the synthesis and the chain length. So you have very less batch to batch variation. And you can also go for natural macromolecules or biopolymers. So some things like collagen, gelatin, silk fibrine, etc., which having a very good biocompatibility and biodegradation properties. So, but then as I in case of the cells or in case of biochemical factors, so similar thing in case of biomaterials. So there is nothing called a universally accepted biomaterials for tissue engineering or regenerative medicine in general. So we have to have a very careful consideration of choosing a material and depending on the tissue of interest. So for instance, if you're talking of corneal related applications, so cornea is a transparent tissue, but it's also mechanically very tough. So you need some material which is giving you that transparency as well as mechanical tensile properties. So then you can think of some spinal fixation screws or spinal fixation cages. So where you need more of a hard tissue based, and you need not have a bioresorbable in that case. Then you can also think of some neuro related applications or now regeneration applications, where you need a scaffold with some sort of a electrical conductivity. So you have hip joints, or you have dental fillers, you have tendons and ligaments which are having a very elastic or tensile properties. So depending on the tissue of interest or depending on the requirement, you may have to choose one or more biomaterials and make a composite and fine tune the properties according to the requirement of the tissue. But then there are certain benchmark characteristics which are supposed to be met by any of your implant material. So the first and foremost, then these are like as per ISO standard. So there is a standard ISO 10993. So that is a benchmark standard for medical devices and other biomaterial based applications. And it says that the material should be tested for cytotoxicity, and it should be non-cytotoxic in nature, because the cell is the fundamental unit of life, and anything which you put into your body, so it's going to react with the cells in a good way or bad way. So it has to be tested, and you have to make sure that it is non-cytotoxic. And then it also need to be non-thrombogenic, because whenever you do a simple cut, the first thing that comes out is the blood. So you have to make sure that this blood interacts positively with your, or in a neutral way with your biomaterial. So if it is reacting negatively, so it would go and attack the biomaterial, and you would have a thrombus formation and clotting, and all the infiltrator, the blood cells will come in, and you will have a graft rejection subsequently. So it should not elicit any sort of a thrombogenic reaction. So the blood material interaction is also very important. Then you have the non-immunogenicity also as a criteria for a material to be accepted for medical application. So it should not elicit any macrophages or T cells or other immune related cells. It should not cause any such of immunological reactions in the body. Apart from this, you can also think of making your biomaterial bioresorbable depending on the interest. So if you are thinking of the wound healing applications or a contact lens or other related applications, you would go for a material which can slowly resorb in the body, and eventually your native tissue matrix will come into come and replace the material. So, but this may not be a universal requirement. So in case of spinal fixations or bone related applications, so people use metallic implants which are not bioresorbable, so which may not be required. So if it's only the purpose is only to give a support, a structural support, so you can still manage with the metallic implant, so you can stick to that, and you need not really bother about the bioresorbability there. Then the other thing is bioactivity. So as I just mentioned previously, that the cells require quite a good number of bioactive molecules for them to work in both good and bad ways. So you have to incorporate these growth factors, of course, obviously the good ones, into your scaffold of interest in order to get a tissue reaction in a positive manner. So that is what you incorporation of the biological factors into your scaffold makes it bioactive. Then you can also think of bioresponsive. So you can load your growth factors, but you don't want to waste that unnecessarily. So you want it to react or to release only upon there is a signal, only when there is a need. So you're thinking of some insulin releasing sort of a reservoirs. So only when there is a need, and depending on the requirements, so depending on the food intake, you want that insulin to be released. So these sort of responsive or smart biomaterial systems also can be, thought about in this field. So, but again, the bottom line is like there is no universally accepted biomaterial. So every material has its own advantages and certain limitations. So depending upon the tissue of interest, one need to choose a biomaterial or one or more biomaterials. But then you can always have to check with international standards for certain criteria before going further. So those are the three components, and let me give you a brief uh, concept or a brief detail on the two approaches of tissue engineering. So the first one is called the top-down approach. So this is a classical approach. So where you have a porous scaffold, so you can think of a spongy material, let's say, and then you have and you want to develop a liver tissue or a sort of a skin tissue or any other tissue of interest, and you take the cells. So in this case, if it is skin cells, so you take fibroblasts and epithelial cells, and you try to seed them on that scaffold. And what the cells do is they attach to that particular scaffold, and they try to penetrate all through your porous network. And eventually, when you culture in vitro for some times, it will give you a tissue, engineered tissue in vitro. So Unfortunately, in this classical approach, so there is something called a diffusion barrier for the cells which are deeper inside the scaffold. So a cell would be able to take gases, or I mean, take oxygen from the medium and take the nutrients from the medium only within 200 microns barrier. So beyond 200 microns distance from its membrane or cell boundary, it won't be able to reach out to the medium and to the gases inside that medium nutrients. So unless you provide a very porous network connecting highly vast or porous network in this case, and unless you provide a dynamic culture system which requires the bioreactors and etc. etc. So the cells inside, deep inside the scaffold won't be able to survive. So this actually leads to what is known as a necrotic core. So only the cells on the periphery will be able to be viable, but only the cells in the center or the cells at the center would be dead. So this is the classical top-down approach, and this is the major problem with this top-down approach. So unless you have a highly porous network, and unless you don't use a dynamic culture system, you won't be able to really achieve a functional tissue in this case. So in contrary to that, there is another approach called bottom-up approach. So here, in this case, there are multiple approaches or multiple strategies, let's say. So where the cells are assembled either in the form of the sheet or in the form of a small aggregates or in the form of an encapsulated systems, or you can even think of this cell printing or bioprinting applications. So all of them are trying to make a small scale micro tissues by assembling the cells in various combinations, and such micro scale tissues will then be assembled in a modular fashion in order to give a macro level tissues. So some approaches in this case use biomaterial. So in this case, this is a hydrogel based system. In the bioprinting also you use a biomaterial, whereas cell sheet technology or cellular aggregates doesn't require a scaffold. So these are scaffold free bottom up approach, and hydrogel based or bioprinting based are called scaffold based bottom up approaches. So this is to give you an idea of the advantages of the scaffold-based conventional tissue engineering strategy. So there is a problem with the initial cell density, as I mentioned. So you have a porous scaffold and you try to seed you pour 1 ml of culture medium on top of it, which are having 1,000 cells, but the medium leak through the porous scaffold, and with that, out of 100 cells, you may lose 50 cells in that particular medium. So there is no control over the cell density. So there is a loss of cell density in this case. You can fine tune the mechanical property of the scaffold, but then there is no possibility of self assembly in the conventional tissue engineering approach. You can functionalize with biomolecules by surface functionalization. The scaffold free strategy, which is in this case cell sheet and aggregates. So here you have a very good control over cell density, but there is a poor mechanical property because cell aggregates and cell sheets are without any material. So they are very fragile and very fragile to handle with. You can think of a self-assembly. You can actually develop multiple cell type based aggregates, but then there is no material. So obviously there is no question of functionalizing those systems with the biomolecules. Whereas the synergistic strategy, which is hydrogel based systems or 3D bioprinting systems, have all the advantages of so you can exactly control the cell density. So if I take 100 cells in a hydrogel system, I am very much sure that all the 100 cells are there in the gel. There is no loss. I can fine tune the stiffness of the gel in order to fine tune the mechanical property. I can also self-assemble those hydrogels by in a layer by layer fashion or other modes of assembling. I can also introduce biomolecules into the hydrogel in order to make it functionalized system. So that is why the 3D printing or this sort of additive manufacturing technologies have really taken the front seat in this particular field. So having given you the background of tissue engineering and 3D printing, so let me take you through the 3D printing versus 3D bioprinting. So 3D printing is an additive manufacturing process. So where you add material in layer by layer fashion, and you try to cure it by different modes, either through physical modes or chemical modes, etc. And Mr. Charles Hull, so he's the person who was behind this entire technology, and initially he labeled or termed it as stereolithography, and he has commercialized the 3D first 3D printing technology in that field. And this is the schematic again giving you the beauty of additive manufacturing as compared to the subtractive manufacturing. So in a conventional CNC machining or subtractive manufacturing, as you most of you know, you have a material and you try to drill out the unnecessary part by subtracting that material, and you would end up having your design of interest, but you end up also having a significant amount of waste. So also you may have a design, but you want really intricate designs, very complex architectural features into your object. So it may be really challenging with the conventional subtractive manufacturing process. Whereas in the additive manufacturing process, you design the object through the computer, and you also manufacture that particular object through the computer in a layer by layer fashion, and you would get your object of interest without losing much of your raw material. And you can also think of very intricate design details into that particular three-dimensional object. So depending on the resolution of the printer, you can even go for a sub-micron level printing resolution. So that is where you get a edge over the conventional subtractive process. So typical 3D printer that we see in our day-to-day life or even advertisement. So you have a filament which is a polymer filament, and it is fed through a heating head, which is typically a heating kind of a mantle, and so there the polymer gets melt, and then it comes out through what is known as a nozzle. It extrudes through the nozzle, and it liquefies, but and then it gets collected on a stage. So as soon as it gets deposited, so again you have a mechanism to cool down and then solidify that particular polymer. So the print head as well as the stage is controlled in X, Y, Z directions by a computer. So it's basically a robotic, dispensing system where you have a control over X, Y, Z direction, and where you have a polymer which is being made it into a soluble form by a heating system, component. So when you add the bio aspect of it, so things get complicated. Of course, things also get very interesting. So the first thing that comes into mind when you think of bio is a sterile environment. So you need to put everything, all your setup in a sterile environment. So you need to have a laminar, a biosafety cabinet or systems like that, or a HEPA filters and etc. etc. Striking feature of bioprinting is the temperature. So you don't deal with 200 degrees or anything of that sort. You mostly deal with ambient temperatures, or to some extent cooling temperatures, or up to maximum 37, because this is the physiological temperature, and beyond that the cells would simply die. So you have a print head which is having an ambient to 37 degrees, not 200 degrees. Then you don't have a polymer filament, rather you have a syringe which is filled with bio ink. So bio ink is nothing but your hydrogel, which is encapsulated with the cells of interest. So I'm talking about skin, so I would have a bio ink, which is nothing but a hydrogel loaded with some fibroblast or epithelial cells. Okay. So then you simply have your nozzle, which is again similar, and then you have a collecting stage, which also can be controlled, temperature it can be controlled. Then you can go for air pressure, so it can be pneumatically controlled or piston based or any other system. So that's also a common feature. But most striking would be your replacement of plastic with a bio ink, having a sterile environmental system, and doing all the sort of experiments at ambient to 37 degrees. So this is a timeline to again historical events. So it started like from early 80s. So there's here Mr. Hideo Kodama. He invented the additive 3D method in early 80s. Then, as I just mentioned, so Mr. Charles have proposed or invented the concept of stereolithography. The first patent was filed in 86, and then you have first stereolithography 3D machine, which is commercially unveiled in the year 1992. Then we have the Wake Forest Institute for Regenerative Medicine, which is a pioneer in the field of 3D bioprinting, especially. And it has started its functions in the 1990s. And then we have something called a self-replicating 3D printer, which is unveiled in 2006. So a 3D printer can making another 3D printer. You also have varieties of or other strategies of 3D printing, such as first inkjet printing being unveiled in the year 2009, and then you have emergence of high-tech 3D printers, multi-head printing or multi-mode combinatorial systems, which you have a 3D printer merged with a electrospinning system and other combinatorial approaches taking in place. So and it has started from simple steps, and we have in fact very good advancements in the field of bioprinting, and Wake Forest is particularly is doing great in the bioprinting of tissues. And in India, many of the laboratories are also proving their presence by developing varieties of tissues, and some of them are also in the phase of advanced stage of preclinical evaluations. Typical 3D bioprinting workflow involves a couple of few steps. So step one would be like you have a patient having a defect. So you start with imaging that particular defect tissue. You try to get an image and then try to simulate and try to make a G code or try to make a design which perfectly fits to that particular defect site. And then you go with for the selection of the material. So what kind of a polymer that you should be taking? So you can have synthetic material, you can have natural material, or you can also go for a biologically derived systems, something like extracellular matrix based components. The next step would be the selection of your cells. So as I mentioned previously, so whether you want to go for a somatic cells from your own body, or you want to take somatic cells from other persons, or you want to go for a stem cell. So that's again has to be decided. And then the actual 3D bioprinting process comes into picture. So you take the cells and encapsulate in the material and try to print and make a three-dimensional object. And then you go for a in vitro maturation process. So because 3D bioprinted construct as such cannot be just implanted into the body, because it doesn't have the histological features and the mechanical features that your target tissue is actually required. So you need to do a in vitro culture in order to mature that particular tissue. As far as the printing machine software is concerned, so again you have your raw data, then what you develop something called a .stl file or a stereolithography file, and then there is a software which actually slices this particular three-dimensional models into different layers. So this is called a G code, and this is fed to the system, the 3D printer software, and you have the bio ink getting printed in that layer by layer fashion and giving you the object of interest. So all three things comes into picture. So you will have cells, you will have growth factors, and then you have this adogel, which is fed into this print head. You can have one print head, or nowadays even the advanced systems will have up to 4 to 6 Hello.
Yeah.
Yeah,
Please
I
go.
hope. Yeah. Okay. So you can also have multiple print head depending on the tissue of interest. So if you're talking of skin, for instance, so you have two layers. So you have a dermal layer, and then you have an epidermal layer. So you can have two print heads, one loaded with fibroblasts, another loaded with epithelial cells. So you first print the dermal layers with print head 1, and then you go for the epithelial layer by using the print head 2, which is carrying the epithelial cells. So And nowadays, the systems are coming with a very sophisticated control. So you can even control, or you can even develop varieties of designs, and you can actually develop modular assemblies, including the vascularization aspect of it. Coming to the strategies in the field of bioprinting, so there are three major approaches. So the first one is the extrusion printing, the second one is the inkjet printing, and the third one is the laser assisted bioprinting. So the extrusion bioprinting, as the term indicates, so it actually works in the by using some sort of a force to extrude out the bio ink from this syringe. So you can actually have a pneumatic control system. So we can just push it by pumping pressurized air. You can also go for a piston-based systems, which you have a mechanically piston which is trying to push the material from behind. You can also think of some screw valve based system where a screw gets continuously rotating, and in the process the bio ink comes out and extrudes through that nozzle. So all three mechanisms are available, but the most popular is the pneumatically controlled extrusion bioprinting systems. The second strategy is called inkjet bioprinting. So these are like on-demand, sort of a drop-on-demand sort of printers. So they, instead of filaments, you can actually have droplets of your bioprinting or bio ink. So this actually have two mechanisms. One is called the thermal-based systems, where you have a heating component in that extrusion nozzle, where it actually try to create a vaporized bubble which breaks the continuity of the flow and thereby leads to the formation of droplets. So you have a drop, you have a continuous filament, but then because of the bubble, it actually breaks apart, and then you end up having a droplet. You can also think of piezoelectrical transducers. So these are some electronic based systems which have a, it's more like a gates. So the gate opens and closes depending upon that electrical circuit. And whenever it closes, so the continuity of the flow is disturbed and you end up having a droplet. So there is a discontinuity because of the opening of these gates or valves, and then you end up having this droplet printing. So it may be required for certain applications, so to have these droplet based systems. The third strategy is called laser assisted bioprinting. So here you have a donor slide, some simple holder, and bottom side of it you have the bio ink coating, and then you have a pulse of laser which is being shooted from the top. And whenever this pulse of laser comes into contact with this hydrogel, again there is a vaporized plasma pocket which is developed at the point of attack, and that actually pushes the hydrogel coating from that donor slide, and it actually comes out as a droplet onto the collecting stage. So of course, one major advantage which is being projected for LAB is the fact that it can work with a range of viscosities compared to the other extrusion-based systems. So all three are available, but mostly it is the extrusion-based bioprinting. So the typical bioprinting setup includes schematic of something like this. So again, you have a sterile microenvironment, and you have a print head. You can control it either by piston or pneumatically controlled systems, and you have your syringe loaded with bio ink. And both the stage as well as the print head are controlled by a computer in XYZ process. So the system as such is very simple. It's as I mentioned, it's just you need a few electronics and few mechanics, a few devices to really build up a 3D printer system, which is just to control your XYZ movement. But what is more critical and the deciding factor in the field of 3D bioprinting is the bio ink. So it actually needs to tick a lot of boxes. starting from printability and looking into the bioactivity and the mechanical properties. So one need to look at the way the filament is being extruded. One need to control the shape fidelity, so whether it is retaining its shape or just simply collapsing after printing. What is the kind of printing accuracy that is being achieved with that formulation, and whether the formulation is compatible, whether it is safe for the cells, whether it promotes, whether it has any positive effect on the cell adhesion, growth, migration, proliferation, and whether the porosity of your bio ink or the 3D printed construct is good enough for the oxygen transfer or the nutrient transfer. Otherwise, again, you will have the same issue of necrotic core, just like in your conventional system. So, and then you also think of its stability over time, because when you try to culture in vitro for a couple of weeks or more as a process of tissue maturation, you will be putting all this construct into the medium, which is aqueous in nature. So whether your formulation or whether the chemistry of your formulation works good enough to make it stable, over those few weeks of culture, and whether it is strong enough to withstand the applied forces. So, you want to handle it with a forceps. So you're applying a force, whether your cell construct would be able to withstand that, or once it is implanted into the patient. So by chance, if there is any uh, strong force applied by the patient or by mechanical or accidental situations, whether your construct would be able to, you know, keep its shape or not. So those are certain parameters one need to really check. I would give you some glimpse of 3D printability assessment in subsequent slides. So as per the applications of 3D bioprinting are concerned, so there are three major focus areas. So the first one is the biological model. So people are conventionally depended on the two-dimensional systems, where we culture cells in a petri dish and we try to see the effect of drugs or effect of certain factors, or try to understand how the cells are proliferating, etc. But then the human body is three-dimensional in nature, and with the advantage of these biomaterials and technologies like bioprinting, people are aiming to develop complex three-dimensional systems by including multiple types of cells. So in this case, for instance, you can take a tumor cell, you can also have stem cell in it, you can have a neighboring fibroblast and epithelial cells, combine them with your extracellular matrix and the growth factors, try to 3D print a construct which is having all these cellular players in that single construct. And then you try to develop a model which is exactly like a native tissue. Because when you say a cancer model, it doesn't just include cancer cells alone. You will have resident tissues or resident cells in that particular tissue, and it will have a highly vascularized network. So that is what people are trying to recreate and try to understand the interplay between various types of cells, whether what is the effect of stem cells, what stem cell is doing to tumor cell, what tumor cell is doing to a fibroblast, what fibroblast is doing to endothelial cells. So multiple sort of interactions can be tracked upon using these constructs. The second focus area of 3D bioprinted construct is toxicity or toxicological application. So you have a lot of chemicals which we use in our day-to-day life, either for personal care or for medical applications, or for, by accidentally we come across certain hazardous chemicals. And we also use a lot of industrial chemicals in industry as well as agri sector. And uh, conventionally, these commercial or industrial chemicals are tested on animals, and but because of the significant protest by the animal activists, and the government is very serious for trying to let's say encourage the alternatives to animals. So that is where the in vitro toxicological systems are coming into the picture, and compared to the conventional two-dimensional platforms. So the three-dimensional bioprinted constructs are really taking the significant step ahead, and so they are able to recreate these three-dimensional models for toxicological testing. So this is also one focus area which is currently in focus. And the third and the most important is the clinical application. So you have quite a few, I think, products already being tested in clinical evaluation, and some of them are already in the market for clinical applications. So starting from implants, dental implants, or even you can go for surgical models. So how to prepare for a surgery. So surgeons are also trying to take the help of these 3D printed constructs in order to find the best possible way to do a surgery. Both the cell-based as well as non-cell-based constructs are being used in the field of medicine. Then comes your 3D bioprinting at our institute. So let me just give you a few studies which we are taking up in our institute. So we have a couple of projects. So, but I would just take the help of give you just a skin-based bioprinting. So we have one project which is funded by DST, and this is mainly for wound healing related applications, as well as to create a toxicological testing services. So skin, as you know, we have a two component systems. We have a dermal component, which is mostly dominated by the extracellular matrix, which is collagen in nature. Excuse me, 1 minute. Yeah, sorry for the interruption. So skin, as we can see here, so it is a bilayered or bi-component system or biphasic system. So you have a dermal layer and you have an epidermal layer. And we wanted to recreate the this tissue histology by developing or by incorporating dermal cells as well as that epidermal cells using some bio-ink formulation. And we have used something called alginate and gelatin based bio-ink. So these are again natural polymers, and these are biodegradable polymers and biocompatible. And as you can see in this picture, so this is a stereo zoom microscope image of your 3D printed construct. This is a single stack and this is a multi-stack. So multi-stack, which means it's a multi-layered construct. And this is a side view, as you can see. So this is one horizontal, one vertical layer. It's a single stack. This is a 3-stack system, and this is a 5-stack system. So which means there are 10 layers on top of each other. And here we just try to print it in multiple shapes just to show the versatility of the printer that we were using. So let me give you some details on uh, sorry, I'm unable to move the slide.
Can you check again, please?
Yeah.
So audience or the people, please don't write on the slide. That will confuse the.
Yeah, I think.
Yeah, some people are writing on the slide. Make sure that you don't write. That will disturb the speaker. Thank you.
Are you able to see now?
Yes, yes. So you can.
Okay.
Yeah, full screen.
Yeah.
Fine now.
Okay. Yeah. So let me give you some, if not all, aspects of printability, especially in the field of 3D bioprinting. So printability is the capacity to form and maintain reproducible 3D samples from bio-ink. And there are various aspects of it. In fact, there is no hard and fast rule, but people are trying to introduce their own version of a printability assessment, and that's how the field is also evolving. So if you have in fact your own ideas, you can even in fact include those sort of parameters, and that can be eventually be useful for the next generation bioprinting researchers. So the first and foremost is something called extruding filament or extrusion analysis. So typically when you have your hydrogel, so it is a semi solid sort of a system, and as soon as it comes out through the nozzle, so typically you would have some clumpy like formulation. So that is not good, or it could just simply drop out from your nozzle without any control. So that's also not good. So just like honey, for instance. So it should come like a smooth controlled extrusion filament, but not like a uncontrolled filament. So you should have a very smooth, very fine filament which is coming out of your nozzle only upon a particular control. So if you press that pneumatic vessel or valve, or you are pushing that piston, it should be able to come out as a simple filament. But as soon as you stop that force, again it should stop. It should not just leak out, just like your honey or some other syrup. So this is the first indication that one should get by about the bio ink. So as soon as you see that it is coming very neatly like a smooth filament, you are almost certain that you got a very good formulation. So then you can go ahead with further analysis. So if there is any crumpy or any sort of a clumpy formation, or if it is just losing out or leaking out uncontrollably, then you need to work out on that formulation before you actually proceed further. So the second component or the second parameter that is proposed in some literature is known as dispensing velocity ratio. So what happens is your machine is XYZ controlled by a computer, and you have a CAD design. So you try to design something, and your machine is also try to print it. But whether the printing velocity, whether the movement of your print head in XYZ direction is in match with the the design that you have given, and whether the printing is happening perfectly according to the design, which so that you would be able to understand when you superimpose your printed construct on top of your design of the original CAD design. So if the printing speed is too fast, what happens is this gets extended beyond your design. If the printing is too slow, you may not be able to actually reach up to that point. So it may immediately take the next turn and start doing the next printing. So the velocity, if it is slow or if it is fast, you may not get a design, or you may not get an object which is a mirror image of your design. So you need to every time print and then check with your design whether you got your original object according to the scale. Okay, so you gave a 1 mm by 1 mm square, and once you have printed, whether the velocity of your XYZ movement of your printhead and the stage, is it good enough for the superimposition of your object with the CAD design? So that is something which is known as the dispensing velocity ratio. Then the third component or the third parameter is proposed is filament collapse test. So this is again we have a in-house made construct, which is a vertical pillar-like structures with a gap of 1 mm, 2 mm, 3 mm, 4. So there's an incremental gap from 1 mm to up to 5 mm. So what we have done is we have printed the filaments on top of these pillars. So when you view it from side, you can see that all the filaments are almost straight. There is no sort of a hanging phenomena which is happening in this between pillars. So the gap which we have proposed here up to 5 mm, it is able to withstand or self-stand on these pillars. So there is no drooping of or any hanging effect of these filaments. Probably after 5, maybe if you are going further, maybe 10 mm or so, you would see some sort of a fall, and that is where that is the indication that you won't be able to build a 3D structure beyond that filament gap. Okay, so this basically gives you an idea of how much width or how much gap I can give between two layers when I am printing multiple layers. So what is the gap that I should be giving in so that it can self-stand without collapsing? The fourth aspect is called assessment of printability angle. So again, we conventionally print a square sort of a box, but then three-dimensional human tissues. If you're considering a customized 3D objects for patient-specific defects, you always don't have the pleasure of making beautiful circles or squares. So you may have to fine-tune various, you may have to, manipulate with various angles. So as a proof of concept, you can actually design multiple like shapes like a circle or a square or a triangle, and then you see whether you are getting that perfect circle-like shape or a square-like shape with a perfect 90-degree or a triangle with a 45-degree. So you can actually see whether you are getting the angles correct. Then there is something called a line spacing alignment or assessment. So this again is a concept just to understand what is the width that I should be giving, because I will be using a nozzle which is having the 450 microns or 500 microns. Then I have another nozzle which is 800 microns. I may have another nozzle with 1.5 sort of an microns nozzle. So when it extrudes out, I cannot just keep same 500 microns between, because when the filament comes out, it actually expands and it will try to encroach the other neighboring free area. So what happens is, when you, although in the model you see that it's a straight line, but the straight line doesn't indicate the width of the nozzle that you are using. It's just a straight line in the design. But when it actually comes on print, here you give 1 mm of gap, but actually, this 1 mm by 1 mm is totally collapsed. It just fused everything together. You don't see any gap as you see in this your model. So what this is a design which is again a cascading sort of a or an incremental gap. So starting from 1 mm square, 2 mm square, 3 mm square, up to, like, you can do multiple boards or checkerboard type of things. And this is the actual print. So when you actually look at the through the stereo microscope, you would see that this 1 mm by 1 mm gap which I have given is simply collapsed. So this is giving me an indication that the width or the interfilament gap that I have selected here won't be working in reality. So I may have to go with minimum of 2 mm by 2 mm gap, so that I can get a construct with a very good porous structure leaving behind, which is necessary for bioprinting or biological application, because the exchange of medium and the nutrients is very important. So there is another element called filament details. So of course, these are again, this is not just one aspect. So there are multiple aspects to it. So I just try to show you three factors. So the first one is called a printability factor. So just imagine drawing a square. So you have a area of that particular square. So, but in reality, you won't get a perfect square. So what you have to do is you have to draw a line along the edge of your printed construct, and you try to calculate that area and divide that by a square area that is the calculated area. So you're just trying to correlate the theoretical area versus the actual area, and you try to see if it is divided by both are divided by each other, you would get, if it is an ideal print, you would get a value of 1. So anything less or anything more indicates little bit of a deformation, but there are always a tolerance limits. So beyond the tolerance limits only you have to worry. Otherwise, it is still okay to have a plus or minus of some tolerance limits. So the point is that you have to just calculate the area of this particular port that you print with the theoretical value. You can also think of how smooth your filament extruded. So it is again simply done by calculating the length of the filament edge. So typically, if you draw a line from A to B, if I'm drawing a line from A to B, so this may look about 1 centimeter or 2 centimeters. But since it is wavy in nature, so it actually adds up a little bit more to that particular filament. So the area of theoretically calculated area, if it is 2 mm, but because of the wavy nature of the construct or the printed filament, you will have 2.1 or 2.2 something. So again, when you divide the actual versus when you correlate the with filament length, actual versus theoretical. So if it is one coming to one, so then it's a perfectly smooth filament. So there is not much of a difference. But if it is more than one or less than one, then you can say that it's not a perfect fit. But again, there are tolerance limits, so you can still manage with a little bit of a wavy nature also. That's not a big issue. But this is one aspect that you can also think of calculating. And another important thing is the filament crossover. So as whenever you print one horizontal layer and then you try to print another layer in a vertical mode on top of the horizontal mode in order to build a three-dimensional construct. So and this is a hydrogel, so it is a very soft jelly-like material. So the point is that if the gel formulation is not optimized well, the second printed layer uh, could potentially fuse with the first layer or the bottom layer. So the top and bottom, how far they are able to stabilize themselves without fusing can also be studied by calculating the width of the filament. So when there is a smooth filament coming out, so you can take the width of the filament in the middle point where there is away from the junction point, and then you also take the width of the filament at the junction point. So that actually indicates, because when if the filament is getting fused, it could bulge to some extent. So there's a the fusion point, and there is some sort of a width increment happening at that particular junction point. So if the filament width and the at the center away from the junction point, and the filament width at the junction point, again when you correlate, if it is giving you a value of 1, so that is definitely a perfect printed filament. There is no crossover at all. There is no fusion of your uh, filament or the bio ink. But if there is a value is a little bit of a not one, whether it is one be above or below one, then that indicates that your bio ink still need to be optimized. You still need to work out so that it doesn't fuse. But again, there are some tolerance limits. So again, it depends. And you can also think of some complex calculations like multi-layer printing. So when you have this one stack, so one stack is one layer of horizontal lines plus one layer of vertical lines.
So, Professor, voice is not clear. Can you, Professor Naresh, voice is not clear. Can you check? Hello, Professor Naresh. So voice is not clear. Can you please check? So, yeah. So, Naresh Garu, so we are unable to hear you. Can you see, check, please? Audience, can you able to hear him?
No, sir.
Yes, sir.
No, sir.
Yes,
Sir,
I'm not here.
No, sir, we cannot hear.
Ravi, sir, better you may call him, sir.
Yeah, please cross check. Yeah, I called him and he is checking, please. Audience.
Thank you, sir. Thank you so much.
Hello, can you hear me now?
Yeah. Now it is audible, Professor. You can go ahead. Yeah, now you can go ahead, Professor.
Yeah, can you hear me now?
Yes.
Yeah, great. Okay, great. I think so. I hope this was covered.
Yes.
Yeah, okay. So I'll move to the in vitro and in vivo analysis. So here in this case, this is just a micro CT image of the 3D printed or 3D bioprinted construct. And as I said, we have cells in it, so we just need to check the viability of those cells. So this is a fluorescence microscope image of cells encapsulated in that 3D printed construct. So the green indicates the live cells. And I'm not sure if you are able to see, but this is a dual staining construct image. So you have some green colored cells, which are fibroblasts, and then you have some red colored cells, which are epithelial cells. So this indicates that dermal epidermal construct, but then we have got a better clarity in the histological staining. So we did some HE staining. So this actually gives an indication or idea of the dermal epidermal phases which are seen here. So this is our 3D bioprinted skin construct. So this is the dermal component where you have a few fibroblasts, but mostly the matrix. And then you have this epithelial layer or the phase where you have a very dense population of epithelial cells on the top. So we have done quite a few some molecular level analysis in order to find out the gene level, gene expression and other aspects of it. And then we finally also did some in vivo studies in the rat models. So we have developed a wound. We have created a wound by cutting a portion of the skin. And then we have, this is the 3D bioprinted construct with cells in it. And as you can see, it is beautifully fitting that particular defect site. And we have closed the wound by using some, a supporting mesh with the sutures. And after a couple of weeks, we can see that the 3D bioprinted construct has completely integrated and the wound is healed very beautifully. So that's just a case study of the kind of printability assessment and the kind of in vitro, in vivo level experiments that we undertake. So this can be applied to any other tissue of interest that you would be interested in. So only thing is that there are certain battery of tests that one need to follow according to some international standards. Plus, you can also perform other studies and characterization assays as per the interest of your academic interest. So that's basically it. And just to summarize, the bioprinting is not just a fancy technology, but indeed a very exciting technology which offers
hope for a personalized medicine as well as a precision medicine. So we can actually customize the therapy according to the patient requirements. So with this, I would come to the acknowledgement section. So the 3D bioprinted skin project is led by Dr. Anugya Bhatt, and I am one of the co-investigator in the project. And we have a good team of staff and students working in this 3D bioprinting skin. And as I mentioned, the project is funded by DST, so we are thankful to the funders. And thanks to Dr. Ravi for giving me this opportunity to showcase some of the basics and some of the practical aspects in the field of 3D bioprinting. And thank you all for the patient listening. I'll be happy to take any questions if any. Thank you.
Thank you, Professor Naresh. And now the audience, thank you for your kind patience. And on and off, we have some glitches which are not under our control of either speaker or either organizer. So if you have any queries, you can directly raise the questions one by one. Thank you.
Hello, sir. Myself, Venkata Krishna, sir.
Yes, please.
Sir, as you said, we have used alginate and gelatin for wound healing applications, right? So what are the standards you followed for characterizing the mechanical properties?
Yeah, so mechanical properties in this case, for not much, like we did some tensile testing thing, but because this is a very soft material, so we haven't performed any, followed any standards, because there are no significant standards for the skin properties as such. So, but we were more interested in optimizing the bioink formulations, working out the chemistry of cross-linking more than the tensile properties or the mechanical properties. But we did one experiment just to show that we have some elastic nature to it, but it is not as per any standard.
So if you want to do means, is there any suggestions you provide, sir? How can proceed?
Yeah, actually there are some ASTM standards, as you may be aware, but they're not particularly concerned, like, because see, for any mechanical testing, as you know, we have to do a mold, so we have to make the material in that dog bone shape or some other recommended shape. So in case of bioprinted constructs, we can make into that particular thing, but the thing is, it's a hydrogel. So when we try to clamp the material onto your tensile testing machine, it just simply crushes everything together. So that's the problem with the hydrogels. You can't. So what we do is we more of we sort more towards rheology analysis. So we do some rheological analysis for checking out the the storage modulus and the other rheological properties. But for metal-based or ceramic-based or other polymeric-based systems, of course, we can go for that ASTM standard. We can make the material in terms of in the shape of a dog bone and then do the test. But for hydrogel-based systems, it's difficult to perform any mechanical testing. We mostly follow the rheology.
So, but for sir, actually, if wound healing applications, it may not be important. But when you go for nerve conduits and all, the elastic properties are more important. So in such cases, what we can do, whatever the polymer standards available, that we can follow.
Right. Yeah, I'm not very much aware of the tissue-specific kind of standards. So, but what I can suggest is probably you can make a construct, let it mature, and then try to test it by other testing things such as indentation or maybe through other means like mostly indentation. Probably we can get some idea of the mechanical properties, but as for elasticity and other things, I'm not very sure, like if we can clamp such hydrogels in the first place.
Okay, thank you, sir.
Yes. Yeah. Yeah.
Amay, we are unable to hear you.
I'm sorry, I could not
This
get
is
your
Amay
voice
Dakle.
clearly.
Very nice presentation, sir. Yeah,
Yeah.
good evening, sir. So actually, I wanted to ask, how much is the, like, if we use only growth factors in the biobank, uh, is it possible that we reduce the chances of host body rejection in from the, like, we eliminate the cells and we only use growth factors in the biobank? Do we reduce the chances of host body rejection in case of
No.
3D printed implant?
Yeah, no, there are two things to it. So when you say you would take bioink only with growth factors, you won't take any cells in it. So actually that may not really solve the purpose, because you ultimately require some amount of cells, because when you say cartilage or when you say neural conduit or any other construct, ultimately you need cells, because cells work in tandem with growth factors as well as extracellular matrix in order to proliferate, differentiate, and try to develop a tissue-like structure. So without cells, uh, growth factors alone may not be able to achieve the way the cells achieve. Number one. And number two is the aspect of managing the immunological or host body reaction. That is something which is multifaceted in nature. So just by using some growth factors, we won't be able to completely eliminate, because it has something to do with your material and something to do with your cells sources. So if the material has some, itching, irritating functional groups, so the cells would obviously react to it. And if you are also taking cells from outside or allogenic in nature, so if you take cells from X person and implant it in Y person, so there would be some level of immunological reaction. So you can only use some immunosuppressing drugs to manage the immunological reaction. That is what is being done in clinic. So when you say kidney transplantation or lung transplantation, liver transplantation, so clinicians manage all these immunological related issues with the immunosuppressive drugs mostly. So growth factors alone won't be able to manage it in toto.
So even if we just load our nanoparticles with growth factor and the ink is only composing of polymer nanoparticle loaded with growth factors, that won't solve the purpose as such of like host body rejection issue.
Not really. I mean, see, like for the sake of academic interest, so we do explore quite a few combinatorial approaches of including nanoparticles and nanofibers and other, components. But like that's what, like there is nothing called a perfect combination or a perfect material or a perfect technique. So there's nothing wrong in doing something new and something different. So there's always a scope for improvement, either in terms of processing, in terms of technology, or in terms of the cell-based aspects. So yeah, I would say, like, it's all like there's nothing wrong in giving it a try. And there is nothing called a perfect combination. So we do have to just try and see how best we can achieve. But what I would comment upon in this at this juncture is, as I work in Sri Chitra Institute, we are mostly looking into the translational aspect of it rather than academic interest. When I say this, so I mean that we don't work towards much publications by adding combinatorial or incremental science. So we mostly interested in making very simple things, because just imagine that you are a corporate agent or a CEO of a company, and I come up with a technology where I have to add A plus B plus C, and there is another guy who can do the same thing with A alone. So obviously, you would be more tending towards the guy who has come up with the A idea. So what we need to do is to have an advantage in the overall achieving the overall thing, but then try to keep things very simple so that it becomes commercially viable. So if you add too many things, too many technologies, too many materials, and too many mechanisms into it, it gets complicated not only from the commercial aspect, but also from the regulatory perspective. So there is a agency in India which regulates all the medical devices, including the biologics-based systems. So the more you add, the more complicated it gets. So translating from bench to bedside becomes more complex and time consuming, and sometimes may not be possible also. So my humble suggestion is that there is nothing wrong in trying different combinations in order to get a desired effect, but then try to keep things simple so that the translation aspect of it becomes easier for you.
Thank you, sir.
Yeah.
Good evening, sir. Am I
Yeah,
audible?
please. Yes.
Very good evening, Dr. Naresh, sir.
Yes.
And this is Dr. Vijay Naidu, working as assistant professor in the Department of Mechanical Engineering, Century
Great.
University. Sir, being a mechanical engineer from manufacturing background, what are the research areas where we can focus so that we can give significant contribution in the field of machine engineering?
Yeah, I think manufacturing definitely is a big thing because first of all, we don't have good bioprinters.
Yes,
We
sir.
are dependent on exporters, and these are costing about anywhere between 1 crore to 2 crores a good bioprinter. So that itself is a big challenge. Of course, we have some decent players from India which are now coming up, and they're trying to build their own sort of indigenized systems. But I think there is still hope. There is still room for a sophisticated 3D bioprinters as such, which can compete with international players. So that is one thing. And the other thing is the patient, I would say, bedside the manufacturing. So what we do here is now currently we do 3D bioprinting in a lab, and then we are trying to transport it to a particular site. But if you do something of a point of care sort of systems, so that would also be very useful. So what I mean by is something where you can just put your hand and the construct can be 3D printed directly onto the patient's hand. Or even now people are coming up with something like handheld 3D bioprinters and systems. So this is, I think, definitely which I would say we have a long way to go. And as far as this is only from the biology aspect, but apart from the manufacturing part, we also need to think of this bio ink formulation. So the chemistry people or anybody working in that polymer related aspect, so can also explore the bio ink aspect of the bioprinting.
Okay, sir. Thank you. Sir, one
Yeah.
more question, sir.
Yeah, sure.
Currently, what are the methods people are using to to make scaffolds preparation, sir?
Oh, there are quite a few actually. There are a lot of techniques. So starting from as simple as solvent casting, you just make a solution of polymer and you pour it in a petri dish and leave it. The solvent gets evaporated and you will get a very beautiful film.
Yes,
Film
yes,
itself
yes,
is a scaffold. You can have a porous film by incorporating some salt into it. So that becomes a salt leaching technique. And you
Okay.
can do a freeze drying. So it is something called a lyophilization. So you just leach out your crystallized solvent component of it. You can go for nanofibrous level systems by something called phase separation. So there's something called thermally induced phase separation, non-solvent induced phase separation. So there are multiple things, and then you can also go for equipment-based processing systems or processes like electrospinning. So you need an equipment, and it gives you something called nanoscale fibrous structures. And you can go for the 3D bioprinting. You can go for melt electrowriting systems. So yeah, there are quite a few. There are quite a few, and it all depends on the requirement. So, and it depends on the money that you have ultimately.
Okay, okay.
Yeah.
Thank you so much, sir. Thank you so much.
Yeah, yeah.
Good evening, sir.
Yeah, please.
Sir, I'm Panil Selvam from Coimbatore, PhD College of Technology. I'm student,
Great,
sir.
great, great.
Sir, actually, is there any procedure for vivo testing from government side? We need to get any approvals like?
For what testing?
Sir, vivo and vitro testing.
Yeah. We like no in vitro, in vivo, up to animal stage, you don't really need government approval.
Okay, sir.
For in vitro cell culture, like if you have some sample, and that's what I said in the very beginning, that our institute has this service division. So we do provide those services to the clients or to the academic as well as industrial sector. So that is that doesn't require any government approval, but we do require something called institute level committees are there. So if you are working with stem cells, so there is a committee which is looking into stem cells in our institute. And if you are working with animals, so there will be institute level animal ethics committee. So these committees need to be informed, and we need to get approval from those respective committees. If we are dealing with stem cells, if you are dealing with human tissues, or if you're dealing with animals, or if you're dealing with recombinant system. So there are multiple committees, but this is only institute level. When you go for clinical trials in humans only, the government comes into picture.
Okay, sir. Thank you, sir. Sir, I have other one question, sir. Actually, we plan to make a femoral stem, like a total hip replacement. We studied we are making a titanium or stainless steel 316. These materials still after surgery, sir, maybe 5 to 6 years. This material will damage the cells or tissues around the around this where we placed. So,
right.
Any suggestions or?
Yeah, I think so. This sort of testing probably it requires some maybe some biocompatible coatings onto your metallic implant, or maybe the surface roughness of it. Maybe there is something you can think of, or the charge of it, or you can even think of if there are any leachables that are coming out of your implant which are irritating those cells. So both leachable, I mean the bulk properties. So when I say bulk, probably I mean not really bulk, but the surface level structures like roughness, the charge that you can see if if there is any issue. You can think of number two. You can think of the illusions or that leachables that are coming out. You can do it in a simulated fluids, body fluids, and see if there is anything which is leaching out both in short and long term. And the third is in case if you feel any problem, you can still go for a coatings which are biocompatible. So you can probably incorporate some drugs which would reduce that effect, negative effect.
Okay, sir. Thank you, sir. Sir, actually, I'm making a direct laser energy deposition method because based on each patient's the dimensions, we can plan to re-engineering and we make it, sir. So that is why I'm asking any coating materials.
Sure.
That is what just we instate, sir.
Yeah.
Thank you,
I
sir.
understand that. Yeah.
Thank you, sir.
Any further questions from any audience? If not there, let's thank Professor Naresh for his valuable time, and thank you, Professor Naresh Garu.
Yeah. Thank you. And it was nice interacting with all the participants. And
all these people will be coming next week.
Oh, I see. Great.
Yeah,
have a
Suresh,
good time.
have any question, Suresh?
Yes, sir. Good evening, sir. Thank you for the
please.
opportunity. Sir, this bioink, can we get commercially, sir, somewhere? Any
Yeah,
sources?
there are companies which are now trying to sell these, but they are charging like anything. So just say one syringe which is having 5 ml of your bioink, they would charge some 10,000, 20,000 of, it's too much actually. So that is something we are also working on to develop some bioink formulations which are affordable. So that's what I was mentioning. So even people like you or people working in the field of polymers or chemistry can think of some, formulations, indigenously, which can be affordable by people. Because there are inks from commercial sector, but they're quite expensive.
Thank you.
Yeah.
Yeah, thank you all the participants, and thank you, Professor Naresh Garu.
Yeah, thank you. Thank you. Thank you.
So
Yeah.
thank you, and we are closing the session, audience, and please note that there is an examination on the final day. Okay, so it's a small examination, but still examination is there. Okay, so clearly listen and gain the knowledge. Thank you. Thank you all. Thank you, Naresh Garu. Thank you.
Yeah, thank you. Thank you. Thank you. Have a good evening. Yeah. Right. Yeah.